Okay, so sorry to those who are only watching the recording. Forgot to turn it on until now, but you haven't missed much. Okay, so we have our model. Here we have training data in the form of training labels, training features. We can call this matrix A. We can put all of our parameters together into a vector beta, and we can define the right side of this approximation as a vector of predicted training labels y hat. So this is what we use to construct our beta vector. Talk about that in a moment. But once we construct it, we can make a new prediction. If you are given a new test vector x, and you can predict the test label y, which is unknown, using your learned coefficients. We'll call them beta hat. And so now we can talk about how we learn those coefficients. So in these early units, we decided to focus on the RSS as our criteria of goodness. So RSS, which is going to depend on how we choose beta, is just defined as the sum over all this is our training RSS, sum of over all our training samples of the true targets minus the predicted targets, that thing squared. You can also write this as the norm of the difference between y and a times beta. And when you minimize this, it's called least squares. So at the time we proposed this, initially we didn't have a very good reason for doing this. It was just something that was convenient. Maybe we've all seen it elsewhere. But now that we've studied a bit more about like maximum likelihood, we know there's actually a way of justifying doing this, which is when the approximation error is due to a noise that is Gaussian and zero mean. In that case, this comes out of maximum likelihood. Maximum likelihood tells us this is what we want to do. Okay, we'll talk about maximum likelihood later. Okay, so back to the least squares story. So to find beta hat, least squares, what we do is we compute the partial derivatives of RSS with respect to each of the individual beta coefficients, and we look for the coefficients beta hat that set that equal to 0. This is for all j we do this. And when we put this all together, we can find that the beta hat vector takes the form A transpose A inverse times A transpose Y. Okay, so we derived this back in lecture 2. So this is how we get our least squares coefficients. All right, so then another thing we talked about was measuring how good our trained model is. Do we know whether we were successful or unsuccessful in predicting our data? So for this, we have our R squared coefficient of termination. And so R squared is defined as 1 minus the RSS over n times the sample variance of our targets. And a few things that we can note about this, I'll write this in a smaller font, is that R squared equals 1 would be what happens if we have perfect estimation, absolutely no error in our predictions. R squared equals 0. We could do that with a trivial estimator that ignores the features and just always predicts the sample mean of the targets. That would give R squared 0. And if you find on the training data that you're getting a negative RSS, there must be a mistake in your code because that is impossible. It's impossible on training data for beta hat least squares. Okay. Now, if you try this, if you measure the R squared on your test data, that could be negative because there could be a mismatch between test and training. Your beta hat works well on the training, but not the test. Or even on the training data, you can build beta vectors that will give you a negative RSS, but the least squares one will never do that. Okay. All right. Any questions on anything so far? Okay. So, so those are kind of the fundamental things we learned. Then we learned a few ways to extend these ideas, for example, to categorical features. So if xj is in like a set ABC where there's different categories, we somehow need to assign this to a numerical value to work with our framework, but we don't want to just set xj to like 1, 2, 3 or something like that, because then we would be imposing some structure on those categories that may not really exist. So what we said is, instead of doing that, we use one-hot coding. And in one-hot coding, we turn xj into a one-hot binary vector. And we saw a couple variations of this. One was what we called coding the intercept. So in that case, each category gets a unique intercept or beta 0. So it's like in your training, for all the rows that correspond to category A, you use one beta 0. For all the rows that correspond to category B, you use a different beta 0. All the rows category C, use a third beta 0, and then you independently fit those beta 0s. That is one way you could do this. There's other approaches as well. You could code the slope of some particular feature, and So maybe you one-hot code the slope of x1. In that case, you're going to use one value of beta 1 whenever that or whenever some other feature is in this category. When that other feature is in this category, for this feature, you're going to use a different value of beta 1 and so on. So those are a couple things. So this is all the same. And then slope. So those are some options. There's other things yes.
And you said for the r squared, it won't go beneath 0, or it won't be negative for the least squares.
On the training data for least squares, yes.
But for like something else, say a ridge, it could be negative?
Yeah, potentially, yeah. Certainly. In fact, like if you think about ridge, as you make the ridge penalty stronger and stronger, it squeezes your coefficients to 0, right? So you can make them as close as you want to 0 just by making that parameter as large as you want. And so essentially, the performance you're going to get is equivalent to the performance where you turn all your coefficients off. So, you can imagine that might give you a negative RSS. Unless, I never really thought about that particular case. So, I don't know, maybe in that case, because if you turn all these off, but then you're still correctly fitting this one, maybe then what happens is you would be creating this to match the sample mean. And so for the ridge case, it might actually be that you are also non-negative. But
On the training.
yeah, on the training. But you could certainly dream up beta vectors that give you negative, which could result from a weird scheme or a mistake in code or something like that. Okay. All right, so that's categorical features. We also talked about other things we can do. Nonlinear transformations used to give new features. So one example of this is polynomial regression. So in that case, even if we have a single scalar feature x, we could make a multiple linear regression model by taking different powers of x and just creating new features from a different power. And you could see that if you had two different features originally, you could do all sorts of things. You could have individually, you could raise them to different powers. You could take the product of them and raise, the first one to a different power, the second one to a different power. There's so many different things you could imagine doing once you allow yourself to do some nonlinear transformations and pre-processing. So after you do that, then the world of linear regression gets pretty big. So anyway, in this case, what we're doing is we are using x sub j equal to x power j. But this is just one example. And this problem motivated us to say, how do we choose D? Because when you do this, when you make up a model, it's not really clear how complex your model should be. Is it better to make it more complex, less complex? And so that led to the next unit where we studied model order selection. All right. Any questions on units 1 and 2? Yes.
When do we choose to code the intercept versus the slope? Like, I know you wrote that earlier, but can you just repeat that?
It's really, you would have to have some knowledge, understanding about the data to justify doing that. So there's no I don't know if there's really a universal method. You could you could potentially include many things in your model. You could say, well, I'm just going to put in one hot coding of the intercept beta 0. I could one hot code beta 1 and so on. And your model, as you do that, your model would just get more and more and more complex, right? Because you just allow more and more possibilities. And so that sort of comes back to this model order selection question. When is it too complex? You hope, now we have a way of thinking about this where it's this bias variance trade-off. If your model is too simple, then the problem is it doesn't have the flexibility to measure what's really happening in your data. But if your model is too complex, we also know that you have too high of a variance. So there's this sort of fundamental trade-off when building a model as to how far do you go in terms of building in flexibility, and eventually it hurts because there's too many things you're trying to learn. So there's no universal answer to that question. But if you know something about the data, some expert has told you, you really got to watch out for this. You cannot assume that this quantity is the same as that quantity. Then you would have a justification for using different variables to model those two quantities. But I would say if you have no justification for using different quantities to model, then you're probably better off using the same quantity, because that will reduce your variance, because you'll have less coefficients to learn. So now we have a way, bias variance trade-off gives us a way of thinking about all those questions and understanding, roughly speaking, these are the problems. Too simple, bias. Too complex, variance. Let's try to find something in between, and let's try to use any sort of existing knowledge that we have about the application, but then let's also use good machine learning techniques like good model order selection, good feature selection, things like that.
Is there a practice exam, or are the homeworks a good example of what questions we would get on this stuff in the exam?
I did post a practice exam this morning.
Okay.
Yeah, it's in. There's a module that has it. So, yeah, and yes, the homework questions are good predictors of test questions. The style of them. Okay. Good. Any other questions? Right. Is this useful to go through this? I think now you can look at it a different way. Maybe you can understand a bit more what's happening with all this stuff, whereas the first time you get a shallower understanding. Okay, so let's come to the next unit then, Unit 3. So Unit 3, about model order selection. We can start by drawing some pictures. Which are just examples, but they kind of help to get the point across of what is underfitting, a good fit, and overfitting. Okay, so let's suppose that we have data set that looks something like this. Let's try to draw it the same, more or less. Okay. So this data is pretty noisy, so it's not really clear what the true model is, but if you come up with a linear model to try to fit this, that's probably going to be underfitting it. If you come up with a model that perfectly passes through all of these points, okay, I didn't, let me try again. Okay, so that model is perfectly matching all the training data, but it's probably not modeling the underlying trend. It's modeling the noise. And then a good fit maybe, maybe something like this. Okay, so we want to model sort of the underlying trend, because when we are in the, once we've trained our model and we're in the prediction stage of the problem, we might be getting new samples that, and I'll draw them as triangles, new samples that are something like these, and those are pretty close to that middle line, but those new samples over here, you know, would not be at all close to that line. And over here, they would be even further away. So, because our eventual goal is to predict the test samples, which we have not seen at the time of training. So during training, if we are really focusing too closely on matching perfectly, we're probably matching the noise, and the noise is going to be different at the time of prediction than it is at training. Okay, so that's the overall, yeah.
Is it possible to overfit like multiple linear regression, or just when you have different exponents of x? Because this is all like polynomial. Is it possible to overfit multiple linear regression?
So I guess it depends. You sort of need to like frame it a little more precisely. So the way that we did it in this unit is, you could, for example, you could say multiple linear regression is this, or as another option, this, or as another option, this. And so in that like nested sequence of different multiple linear regressions, yes, it could be that the true polynomial order was 2, and so when you go all the way out to a higher number, you are. I don't know if that's making sense.
You can have x squared in multiple linear regression.
Well, in some sense, this is just an instance of, like, I could write this as x sub 2 and x sub d, right? So it's like I have a set of different linear models. Some have more coefficients, some have less coefficients. And yes, if I choose one with too many coefficients, I could definitely overfit. Maybe I can get away with one with less coefficients. I don't know if that's what you're asking, but that's one interpretation of your question.
Yeah.
Okay, so so that's sort of what we're wrestling with. And now we talked first about a naive method, which was to look at the training RSS or training MSE as a function of the model order D that we are choosing. So this is I'll write this as hypothesized. So there's some true model order, but the one I'm plotting here is just our hypothesis. And what we saw is that the training RSS is non-increasing. In other words, usually it's decreasing. The larger you make D, it just keeps getting lower and lower. But at some point, maybe you've gotten to the very minimum, maybe you've gotten to 0 when you've matched your training data perfectly, and then of course it can't decrease from there, but it will never increase. So this idea of let's just try different D and see which one works best on the training data, that doesn't work because that will always cause you to choose essentially the largest D that you tried. So that's going to result in overfitting. So this suggests to use the most complicated model, which generally will result in overfitting. So we had to give up on that, but we have a solution. The solution was called cross-validation. And the idea here is choose the model order using samples different from training samples. And by the training samples, we mean the ones used to get your coefficients beta hat. So usually that means taking our data set and splitting it into different pieces. So we had some different options for this. One option was a simple test, train, split, where maybe you take 80% of your samples, you use them for training, and you hold out 20% of your samples and you use them to evaluate the trained coefficients at different model orders D. So one issue with that was you're not using all the different samples for training, nor using all the different samples for testing. So the answer you get is going to depend on exactly which samples you use for training, which for testing, and so on. So as a way of making this a bit more robust, we had k-fold cross-validation. And the idea there is you train on k-1 folds and you test on the remaining fold, and you repeat this for all combinations, or all k combinations, because there's k different ways you could build that test fold, or k different choices of the test fold. So this way, you end up using all of your data at some point for testing and all of your data at some point for training. So it's a bit more robust. But still, even there, it will depend on the exact random split that you use, the training indices that you use to make your different folds. So if you run this once, you get certain performance, and then if you run it again with a different random seed, you'll have a different sets of folds, you'll see different performance. So it's not completely consistent. Scikit-learn gives you something called repeated k-fold, which will actually do this k-fold as many times as you want. So maybe you do k-fold, like 10-fold cross-validation, but then you do this 5 times. So now it has 5 different ways to create your folds. And that's, the more you use, the more consistency you'll get. Of course, it takes longer to do the fits, but that is an option. Okay, so a little bit more detail then. So what we do is, when we do this k-fold process, we create an RSS for the kth testing fold, and let's say for the dth hypothesis of our model. So we create this matrix of RSS values. In order to figure out which is the best D, we typically will just average this over K, and we'll call this RSS bar D. And so this is our sample average of some true underlying random RSS. We can think about this as an estimate of expected value of some true underlying RSS as a function of D. So this is random. Okay, so at the time we introduced these things, it was before we started talking about random variables. So we didn't maybe describe it this way originally, but the idea is that if you do this experiment over and over again with these different random seeds, you're going to get a different value for this RSS bar D every time. You could sort of, if you do this many, many times, you could sort of imagine that this is, on average, it's like many realizations of some random variable RSS bar D. And this is, every time you do the experiment, you just get one realization of that. And so you could say that that's just one estimate of this true thing you would like to compute. And if you had the luxury of running the experiment many, many times, maybe you could actually figure out what this is. Usually we don't. Usually we're just given one data set. That's all we have to work with. So we can do this once. When we generate synthetic data, like in the lab for Unit 3, we could actually regenerate the data 100 times, and we could actually experiment with this. But that's not what happens in reality. In reality, you're just given one data set, so you just have one chance, one estimate of this. So then the question is, knowing that this is just an estimate of this true quantity, it's imperfect, how much should we trust it? And for that, we have the standard error. So let me write this. Okay. But okay. I'm getting a little bit ahead of myself. Let me just say the simple approach to model order selection then is to choose dmin, which is just going to be the arg min over d of RSS bar d. So you just look at your RSS bars over d, and whichever RSS bar is the smallest, that is the d you choose for your model. Okay, so what we saw is that there's cases where there's many different RSS bar Ds that are very close to each other. And so maybe the minimum one, if you did this experiment again, the minimum one would keep changing. And so for any given experiment, you don't really want to trust the minimum one, because you acknowledge that there's some randomness and imperfectness in this RSS bar D. So for that, we have this one standard error rule, which allows us to acknowledge the imperfectness, measure it through the standard error, and then use that in a more sophisticated rule. So for this, we have the standard error. The standard error, I'll put that in quotes, on RSS bar D. This, we'll call it SE. sub d. This is defined as what I'll write now as sigma hat over square root k, where sigma hat is the square root of 1 over k times the sum I equals 1 to k of RSS, actually, okay, I changed my notation a tiny bit to I. Okay, so here we're looking at our RSS bar D from before, but then we're also looking at all the different components that went into making it, and we're looking at how much they vary from RSS bar D on average by looking at the sample variance. And actually, we want to use the unbiased, so let me correct that. There should be a 1 over k minus 1. And so we could think of this guy as I'll put this in red. This is like an estimate of the variance of that random variable with the square root on it. So even this thing is random in the sense that if we perform this experiment over and over again, it would always be a little different because these values are always a little bit different. But it does give us an estimate of the square root variance of our this quantity we're trying to compute, which tells us how much to trust things. So let's see. Maybe if I make a little room, I can fit everything on one page. Okay, are there any questions so far? Anything I've said? Everybody, yeah.
Can you explain why 1 over k minus 1 makes it unbiased?
Yes, so, well, okay, there's a whole handout with a derivation on this. So there's no short explanation, but basically it has to do, it's not specific to this k-fold optimization, k-fold cross-validation. It's just sort of a generic thing. When you have a random variable with a certain true mean, and you see realizations of that random variable, and you try to estimate the true mean by taking the sample mean of the realizations, you can analyze the performance of that estimate. You can say, you can ask the question, does that estimate agree with the truth on average? That's the bias question. And the answer is yes, the sample mean estimator is unbiased. But then you can ask the question, what if I have a random variable with a certain variance? Like it's a Gaussian random variable with a variance of 2. And let's say I don't know that, but I see examples of that random variable, and I'm trying to estimate the variance. And there's different ways to estimate it. So one way to estimate it is to use this equation with the minus 1 there, and another way is to use it without. And if you use it without the minus 1, you get some answer for the variance. It's not going to be perfect. And then the next question is it correct on average? And the answer is no. If you don't have the minus 1 there, it's not correct on average. It's actually a little smaller than than the truth on average. So by putting in the minus 1, you're correcting it and you're making it unbiased. So the sample variance agrees with the true statistical variance on average. That's kind of the short answer. But yes, there is a derivation, half a page derivation. It's important stuff because a lot of the little line by line stuff you're going to see in other derivations. You're going to see it on the midterm. You're going to see it, So that kind of stuff, if you haven't gone through it, I suggest to go through that little handout. It's called On the Bias and Variance of the Sample Estimators. It's all simple stuff with expectations and independence property, linearity property, just, done a bunch of times. So, okay. So, yeah, and the reason why, so when k is large, the difference between 1 over k minus 1 and 1 over k is pretty insignificant. So when people compute the variance from the sample variance using many, many copies, they don't really worry about this. But when k is small, like for 5-fold cross-validations, k is 5, that's a relatively small number, and you will see a difference between 1 over 5 and 1 over 4, right? There's a 20% difference here. So it actually does make a difference, and the tradition, at least for computing the standard error in this case, is to use the unbiased one there. Okay. All right, so finally we can talk about what we're going to do with these quantities. So let's draw a little picture. Okay, so this is the one standard error rule. Let me try to fit it in here. So this is versus D. Maybe we have several hypotheses of D. The dots are the RSS bar. The error bars are showing us plus or minus standard error. And so what we do in the one standard error rule is we first find d min. D min, we look at which is the lowest dot. Where's the location of the lowest dot? That would be d min. Then we say, okay, but we know that this is not completely trustworthy. We know that anything in this range is actually trustworthy. So let's just look at the top of the range. Let's draw a line there. Put this in red. This is what we call our RSS target. We call it RSS bar target. And we say the simplest model that whose dot falls under the RSS target, that's the simplest explanation that is plausible. So let me move this one up a little bit. Oh, it's not helping. Okay. All right, sorry. So let's put the target line there. Sorry, it's not perfectly straight. So the simplest explanation that is under the target would be the one standard error rule hypothesis. That would be this one. Because of all these dots, it's the smallest one. Here, smaller d is simpler. The smallest one that lies below the target. Okay, so so our RSS bar target is RSS bar d min plus standard error d min, and then d1 standard error is the arg min over d of, actually, sorry, It's just the minimum of all D such that RSS bar D is less than RSS bar target. Okay, so that's mathematically, and then this is the simplest. So when you're doing this with lasso and you're looking for the lambda, or let's say alpha is the strength of the penalty, you would actually be looking for the max alpha, because as alpha gets larger, the model becomes simpler. For this polynomial modular selection, as D becomes smaller, the model becomes simpler. So it's important to remember that. You have to think about whether you want to min or max depending on whether the quantity makes the model get simpler or less simple as it gets bigger. Okay, so so did I have anything else? Yes, so there is more to Unit 3, but we could stop here for today and continue Monday. We're a little bit ahead on the lectures, so we can afford to take more time to review. All right, any other questions on anything so far today? All right, enjoy your weekends. See you on Monday.